Today's discussion is for undamped vibration and critical speed of rotor on flexible bearing support. So in this discussion, main points to be discussed or considered are: bearing is considered flexible and hence the displacement of shaft at bearings and also bearing displacements itself are considered. That means there will be displacement of shaft at bearing and also there will be displacement of bearing itself. But the mass of bearing is not considered as it is a smaller than shaft mass and hence neglected. Damping of shaft is not considered being a smaller value. Also damping of bearing is not considered as it is a undamped condition. Then derivation of critical speeds, then derivation of amplitude of bearing, derivation of amplitude of shaft, understanding of bearing stiffness, and then curve of speed versus amplitude for bearing as well as rotor, and amplitude is infinite at critical speed. So these are the points to be discussed in coming slides. Now this is a flexible bearing supported rotor. That means there will be bearing number 1 and 2. There are two bearings where rotor is supported and there will be displacement of bearing are x2. Similarly, displacement of shaft is x1 and the displacement are perpendicular to the direction of axis of rotation of the shaft. So now derivation of shaft equation and derivation of bearing equation. Let us assume the following: the mass of bearing is neglected, shaft damping and bearing damping are neglected, mass at center of shaft is mkg, stiffness of shaft is k1 Newton per meter, stiffness of bearing is k2 is Newton per meter, eccentricity of mass from the center of axis is EU in meter, angular speed of shaft is omega radian per second, angular displacement in time t is omega t radian, lateral displacement of shaft and bearing are x1 and x2 respectively in an x-axis and y1 and y2 respectively in y-axis. Then shaft equation in x direction, m x1 double differentiation plus k1 into bracket start x1 minus x2 bracket close is equal to m into eu into omega square into cos omega t. Similarly for shaft equation in y direction, m into y1 double differentiation plus k1 into bracket start y1 minus y2 bracket close is equal to m into eu into omega square into sine omega t. Bearing equation in x direction is equal to x direction can be written as k2 x2 is equal to k1 into bracket start x1 minus x2 bracket close. Similarly, bearing equation in y direction, k2 into y2 is equal to k1 into bracket start y1 minus y2 bracket close. If z1 and z2 are complex number for shaft and bearing displacement respectively, then equation of motion of shaft for complex number form can be written as shaft equation m z1 double differentiation plus k1 into z1 minus z2 bracket close is equal to m into eu omega square into bracket start cos omega t plus I sin omega t bracket close. But e to the power I omega t is equal to cos omega t plus I sin omega t. So shaft equation can be written as m z1 differentiation double differentiation plus k1 bracket close z1 minus z2 bracket close is equal to m into eu into omega square into e to the power I omega t. Similarly, we can write bearing equation is K2 Z2 is equal to K1 bracket start Z1 minus Z2 bracket close. So these are expression for vibration of shaft, displacement of shaft and displacement of bearing. Now undamped critical speed. The shaft equation m z1 double differentiation plus k1 bracket start z1 minus z2 bracket close is equal to m into eu into omega square into e to the power I omega t. This is equation 1. Bearing equation k2 into z2 minus k2 into z2 is equal to k1 into bracket start z1 minus z2 bracket close, equation number 2. For natural frequency or critical speed, external centrifugal force will be 0. So this in equation number 1, this will be 0. So we can write shaft equation m into z1 double differentiation plus k1 bracket start z1 minus z2 bracket close is equal to 0. This is equation number 3. Assume the solution of the form rotor displacement. We can write z1 is equal to z3 into e to the power lambda t, where z3 is equal to displacement in complex number, lambda is eigenvalue and t is the time. Bearing displacement z2 is equal to z4 into e to the power lambda t, where z4 is displacement of bearing in complex form, lambda is eigenvalue, t is the time. So z1 dash or z1 differentiation is equal to z3 lambda e to the power lambda t, and z1 double differentiation is equal to z3 lambda square into e to the power lambda t. After replacing z1 double differentiation and z2 in equation number 2 and 3, we can write bracket start m lambda square into z3 plus k1 bracket close z3 minus z4 bracket close into e to the power lambda t is equal to 0, and from second we can write k2 into z4 e to the power lambda t is equal to k1 into bracket start z3 minus z4 bracket close e to the power lambda t. But e to the power lambda t cannot be 0, and so we can write the equation m into z square into m into lambda square into z3 plus k1 into bracket start z3 minus z4 bracket close is equal to 0. This is equation number 4, and k2 into z4 is equal to k1 into bracket start z3 minus z4 bracket close is equal to equation number 5. So from equation number 5 we can write k1 plus k2 bracket close z4 is equal to k1 into z3. So z3 is equal to z4 into 1 plus k bracket close, where k is equal to k2 upon k1. So replacing z3 in equation number 4, we can write m into lambda square into z4 bracket start 1 plus k bracket close plus k1 into bracket start z4 into bracket start 1 plus k bracket close plus minus z4 bracket close is equal to 0. So m lambda square into 1 plus k plus k1 into 1 plus k minus 1 bracket close z4 is equal to 0. But z4 cannot be 0, and so we can write m lambda square into 1 plus k bracket close k1 into 1 plus k minus 1 bracket close into z4 is 0, as z cannot be 0, so we can write m into lambda square into 1 plus k bracket close plus k into k1 is equal to 0. So we can write lambda is square is equal to k into k1 upon k upon 1 plus k. So lambda is equal to plus minus I omega CR square root of k upon 1 plus k. So lambda 1 is equal to 0 plus omega CR is square root of k upon 1 plus k, and lambda 2 is equal to 0 minus omega CR square root of k upon 1 plus k. So undamped critical speed omega c is equal to omega CR square root of k upon 1 plus k. This is radian per second. If you want to convert in critical speed, we can write omega CR into 60 upon 2 pi. So this is equation for undamped critical speed on flexible bearing. So now undamped vibration amplitude of bearing. The shaft equation can be written as m into z1 double differentiation plus k1 into z1 minus z2 bracket close is equal to m into eu into omega square into e to the power I omega t. This is equation 1. Bearing equation k2 into z2 minus k1 into bracket start z1 minus z2 bracket close, it is equation number 2. So assume the solution of the form rotor displacement z1 is equal to z3 e to the power I omega t and z2 is equal to z4 into e to the power I omega t. So putting the value, so you can differentiate z1 differentiation, then z1 double differentiation. So after replacing z1 dash and z2 in equation 1 2, we can achieve these equation number 3 and 4. So further analysis and further simplification, we can get that A2 upon EU directly F square upon bracket start K minus F square into 1 plus K bracket close, where K is K2 upon K1 and F is equal to omega upon omega CR. So when speed omega exciting frequency equal to a damped critical speed omega CR, so F is equal to omega upon omega CR. So you can write omega C upon omega CR and can be written as a square root of k upon 1 plus k, and putting in the above equation we can get A2 upon EU is equal to infinity. So amplitude is infinite at critical speed. Undamped vibration amplitude of shaft. Same way we have to derive shaft equation m z1 double differentiation plus k1 into z1 minus z2 bracket close is equal to m to the m into eu into omega square e to the power I omega t, and bearing equation k2 into z2 is equal to k1 into z1 minus z2 bracket close, it equation number 2. So same way I have to assume the solution z1 is equal to z3 e to the power I omega t and z2 is equal to z4 e to the power I omega t. Again z1 differentiation, z1 double differentiation, putting all z1 double differentiation, z2 in equation 1 2, and then simplification, we can get a1 upon au is equal to f square into 1 plus k bracket close upon bracket start k minus f square into bracket start 1 plus k bracket close. This is the expression for shaft amplitude, where k is k1 upon k2, k is equal to k2 upon k1, and f is equal to omega upon omega cr. So when speed omega is equal to undamped critical speed, so f is equal to omega upon omega cr, so omega c is omega cr, we can write square root of k upon 1 plus k, and putting this equation again, shaft amplitude is also infinite at critical speed. Now let us understand about the bearing stiffness. So what is bearing stiffness at each bearing in x direction? Let's say k x is Newton per meter. Bearing stiffness in each bearing in y direction, k y Newton per meter. So average stiffness at each bearing kb is written as 0.5 of kxx plus kyy. So bearing stiffness at both bearing is 2 times of kb, that is whatever the average into 2. So let's say kxx and kyy are 120 to 10 power 5 and 160 to 10 power 5 Newton per meter respectively, and sharp damping is sharp damping 15 to 10 power 5 Newton. In fact, it's not sharp damping. This is the kxx is this value and kyy is this value. Wrongly, it is written sharp damping. It is a stiffness. So one stiffness kxx is 120 to 10 power 5. This and this is not required actually, by mistake it is written. Now calculate this stiffness. Kxx is 120, this kyy is 160, this average stiffness is this, bearing stiffness is this. So stiffness ratio K2 upon K1 is equal to, then this should be shaft stiffness, not the damping, because I have it shown here for calculation. So it should be shaft stiffness, not damping. So we can say 280 upon 55 is 5.09. So this is how, bearing stiffness and sorry, shaft stiffness are related, or stiffness ratio we can call K, which is K2 upon K1. Now bearing stiffness, shaft stiffness ratio, this is stiffness ratio and this is a undamped critical speed ratio. If you see, as stiffness starts increasing, this value is also increasing, and try to achieve towards 1. As long as if you start increasing the stiffness of or bearing stiffness has increasing. As it starts increasing, this ratio is also increasing across to 1. Then undamped vibration speed versus amplitude curve. So the bearing vibration or bearing amplitude, this is speed is the x-axis and amplitude in y-axis. If you see at what is called, this is a resonance area, or critical speed is same, amplitude is infinite, and before this is positive, after this is negative. If you take the magnitude, so both are positive, and this point is infinite. So undamped critical speed on flexible bearing support and 4565 rpm, the amplitude is infinite, because this is a critical speed. Similarly, for the shaft amplitude at critical speed, you see this is infinite. This is axis is speed and y-axis is amplitude. So shaft is infinite at critical speed. So thank you. Hope you have understood about the undamped critical speed or undamped vibration of rotor on flexible bearing support. So thank you for watching.